Okay, change of plans. I know, I lied. But hear me out. I said we were going to use the Hitachi LCD screen next, but I realized something. We've got our Arduino boards zap strapped to our robots and already set up to drive the robot around. Now, it was a lot of work to do this. I also wanted to use our fancy schmancy ultrasonic sensors in tandem with the robot. So we'll do the ultrasonic sensor first because you may struggle to get enough connections for all of your gear with the controls for the robot, all the connections for the Hitachi display, etc. We are going to use that new ping library we just downloaded in the last lesson though. That was why we downloaded it. It's for driving and using this ultrasonic sensor. Okay, so just what is this sensor anyway? These two silver things are actually very high frequency speakers. In fact, they operate at sound frequencies that are beyond the range of human hearing, about the 40 kilohertz range. It might seriously irritate your dog or cat or the mosquitoes in the room. I don't know, I don't have a dog or a cat and it's winter here, so I haven't tested it on mosquitoes yet. You'll remember in the first module, we could use speakers as a microphone as well. Well, that's what they did here. They send out a 40 kilohertz pulse, then switch the electronics to use the speakers as microphones to listen for the echo off the walls or off of obstacles. Now, this shield only has 4 pins, VCC and ground, and then the other 2 pins called trigger and echo. So when you send a high pulse of at least 10 microseconds long to the trigger pin, the board sends out a pulse train at about 40 kilohertz. The sound goes out and bounces off of walls or other obstacles. It echoes. The board then listens for the echo and times it. When it receives the echo, the onboard electronics then send a pulse out on the echo pin, and the length of that pulse is the time it took between the transmission and reception of sound. Now, because we know the speed of sound in air, we can use this as a non-destructive, non-contact way of both detecting objects and measuring distances to that object with surprising precision. Now, the speed of sound in air is about 340 meters per second, or 0.034 centimeters per microsecond, or 0.0034 millimeters per microsecond. The time for the echo is the time it took for the sound to travel both to the obstacle and return. So we divide that time in half, which is the time it takes the sound to travel one way only, and we take that time in microseconds, multiply it by 0.034, and voila, we just measured the distance to the object in centimeters without even touching it. So the applications of this technology in robotics goes far and wide. Everything from navigation to mapping unknown areas, to measuring the distances to your load that the robot is going to pick up, etc. Imagine a mobile robot driving through an unknown cave system with one of these sensors that it can, aim in different directions. As it drives through the cave, it can take measurements in all directions, store those measurements, and actually build a map. It can both build the map and then navigate the map as it takes measurements along the way. This is the principle behind SLAM navigation, which we'll get into in course 5. Simultaneous localization and mapping, SLAM. It is building the map and locating itself within that map at the same time and exploring previously unexplored areas. So what we're going to do is use it again as a proximity sensor, but we'll first use it to actually measure distances. We'll manually drive it so you can see it directly in action. Then we'll use the new ping library, then use it in conjunction with our mobile robot platform for proximity detection. You can see that I've removed my infrared sensor and replaced it with the ultrasonic sensor. I've just strapped it down so the emitters are pointing straight forward. I used the original power connections I was using on the infrared sensor and connected the trigger pin to the Arduino DIO pin 6, and the echo pin goes to DIO pin 7. We're just going to use our sensor as a non-contact ruler for now. I set up the serial print function because we're going to send some data to the computer screen. So in the loop function, we set the trigger pin high for 10 microseconds, then set it low. While that trigger pin is high, and for a short time afterwards, the receiver electronics are locked out by the shield. This isn't just because the electronics have to switch from using the speakers as speakers to then connecting them to amplifiers on the board to use them as microphones. It is also because this whole board will actually shake from the sounds being emitted. So it will give false readings. So once the lockout is complete, the onboard amplifiers start listening for the 40 kilohertz sound coming back as an echo, and timing how long it takes. Now, because of this needed delay and the high speed of sound, the nearest you can measure is about 2 centimeters or just a little under an inch. Now, this can be a little tight for use on our mobile robot, as you can't measure any distances shorter than 2 centimeters. Now, not a big deal, I guess. I mean, just how close do you want to get to that wall anyway? The echo pin will go high after a brief pause, and it will stay high until it hears the echo. If it does not hear an echo within 38 milliseconds, it times out and assumes that any objects out there are beyond its range. So the echo pin then goes low. So taking 38 milliseconds and dividing it in half to get the distance the sound traveled is 19 milliseconds. At 0.034 centimeters per microsecond, our maximum range is about 6.46 meters, or about 20 feet or so. To make things even simpler, some really nice person working with Arduino wrote an instruction called pulse in. Pulse in checks a pin that you name and times how long the pulse on the pin was either high or low. You tell it which way you want to measure. In our case, we want to measure how long the pulse goes high on pin 7. Our echo pin. Pulse in simply returns the time in microseconds. So easy peasy, we cheat and invoke the pulse in instruction right here. We tell it to time the high pulse on our echo pin. I chose to store that time in a variable called echo time, just so you can see the math performed a little more easily. Now, we need to set up our distance measurement as a variable with a floating point decimal point. Otherwise, the math will constantly try to round our numbers and we get erratic mathematical results. So we take our echo time, divide it in half because our sound traveled twice as far as we're trying to measure. It went there and back. We then multiply that time in microseconds by 0.0344 centimeters per microsecond, and voila, we have a distance. We spit that distance out to the Sirius monitor, and there you go. So this is the ultrasonic sample code available in the download section. Go ahead and flash it to your Arduino. There are several limitations here with my very short sketch. For example, if everything is farther away from my robot than 2 meters. It all takes time to take these measurements. And in my particular case, let's say I don't care. I just need to know if there's an obstacle immediately in front of me. I can't really change my timeout distance. So let's now use our new ping library we just installed. The new ping library is pretty impressive. It can ping and measure up to 15 ultrasonic sensors at once. So coming back to that SLAM navigation I was talking about, wow, you can do some pretty serious mapping by putting an array of these sensors all pointing out in a spherical shape. You could map unexplored caves or dangerous and abandoned buildings, all kinds of cool stuff. So here's the sample code provided with the new ping library, but I've modified it for our lesson. The code is available for download in the downloads section. We must first include the new ping library. You've already installed it, so you just need to include it now. And right off the hop, we start transferring data between our sketch and the library, just as if it were a function in our sketch. Now, there are several functions within the new ping library that we can call. In fact, here's the list on the Arduino Playground site. So in our case, we'll use the sonar ping function that's in the library. So the library is expecting 3 variables to be handed to it. Which Arduino pin is connected to the trigger pin on the shield, which Arduino pin is connected to the echo pin on the shield, and the timeout distance or maximum distance you want to measure in centimeters. If you leave that number out, it will default to 500 centimeters or 5 meters. So we send this data over to the library by calling on the library and referencing sonar and then sending the data. Now, of course, what data gets transferred and how varies from library to library. So you have to look up how the library is used. And of course, you can read all of this detail on the Arduino Playground site where you downloaded the new ping library. So we then set up the Sirius monitor to print the results the library sends back. Here's the call to the specific function in the library, and the value returned is simply printed on the serial monitor. So go ahead and flash the sketch to your board and experiment around with measuring distances. Now, notice how some objects reflect the sound waves better than others. Round objects tend to reflect the echo in different directions, as well as objects on an angle. Your skin tends to absorb a lot of the ultrasonic sound and as a consequence, not reflect all of the sound back to the sensor. So you can get some erroneous or erratic readings. So now I leave you with the challenge. You now know how to read distance with the ultrasonic sensor now, and you know how to drive your robot around. So I'll challenge you to the same challenge we did with the infrared sensor. Have the robot simply drive forward, and when it encounters an obstacle, simply turn and back up and proceed in a different direction. In this case, the threshold will be a distance to the object that you determine and measure with surprising accuracy. You can even cheat and just modify your infrared proximity sensor sketch. Okay, so have fun with that.